Understanding the universe is like standing at the base of a colossal mountain. From below, only the nearest slopes are clear, while the summit disappears into the clouds. Each step upward reveals more of the landscape: valleys of galaxies, cliffs of dark matter, and ridges of cosmic time stretching farther than we imagined. This journey is our climb. We begin at the mountain's foot, at the origin of the cosmos, and ascend together toward the broadest view the universe allows. If you're fascinated by the impossible, subscribe and join the journey as we dive into the mysteries of the universe. 13.8 billion years ago, everything we know, from the smallest atom to the largest galaxy, was compressed into a blisteringly hot, dense state. What followed was not an explosion in space, but an expansion of space itself, a stretching of reality that happened with unimaginable speed. Physicists call this inflation, a process that took subatomic fluctuations and magnified them to cosmic scales. Think of it like pulling a rubber sheet covered in tiny wrinkles. As the sheet stretches, the wrinkles grow into vast undulations. In the same way, those initial quantum fluctuations became the blueprint for the grand architecture of the cosmos. Regions just slightly denser than their surroundings would one day pull in gas, form stars, and give birth to galaxies. Without this early unevenness, the sky would be forever dark and empty. Once inflation ended, expansion slowed, and the young cosmos began to cool. In the first seconds, the building blocks of matter, protons, neutrons, and electrons, emerged from the primordial plasma. Within minutes, many of these protons and neutrons combined to form light nuclei, mostly hydrogen, some helium, and a trace of lithium. This process, called nucleosynthesis, set the chemical foundation of the visible universe. Even now, nearly all normal matter is still in the form of hydrogen and helium, with everything else, including carbon in our bodies and iron in our blood, coming much later. For hundreds of thousands of years, the environment was still too chaotic for light to move freely. Photons ricocheted endlessly off free electrons, making the universe opaque, like the blinding glow inside a dense fog. Only when temperatures dropped enough for electrons to bind with protons did transparency arrive. At that moment, neutral hydrogen atoms formed, and photons could finally travel unimpeded. That ancient release of light still surrounds us. Today, we see it as the cosmic microwave background, a faint glow stretched to microwave wavelengths by the continued expansion of space. It acts like a baby photograph of the cosmos, frozen in time about 380,000 years after the beginning. At first glance, this light is nearly uniform, but sensitive instruments reveal subtle variations in temperature, differences as small as 1 part in 100,000. These tiny ripples were crucial. Regions slightly warmer or denser attracted more matter under gravity, amplifying their advantage. Over billions of years, they grew into galaxies, clusters, and vast cosmic filaments. Without these faint imprints, there would be no stars, no planets, no life. For a long period after the release of the background light, the cosmos remained dark. Neutral hydrogen filled space, absorbing and scattering starlight. This era, known as the Cosmic Dark Ages, lasted until gravity gathered enough gas to ignite the first stars. The process relied on something invisible, yet dominant: dark matter. Though unseen, it provided the scaffolding like steel beams in a skyscraper, around which ordinary matter could accumulate. When the first stars finally flared to life, they were unlike those we see today. These so-called population 3 stars were enormous, hundreds of times the Sun's mass, and burned with ferocious intensity. Their lives were brief, ending in spectacular explosions that scattered the first heavy elements into space. With each new generation, the universe became chemically richer, introducing carbon, oxygen and iron, elements essential for the later formation of planets and life. Starlight from these giants had another profound effect. It reionized the surrounding hydrogen, stripping away electrons and transforming the opaque fog into transparent plasma once again. This period of reionization marked the true dawn of galaxies, when light could travel freely across cosmic distances and fill space with brilliance. From here, galaxies began to assemble in earnest. Small proto-galaxies merged and collided, building up into the grand spirals and ellipticals we observe today. Our own Milky Way began as a swarm of these smaller systems, slowly growing into the majestic spiral that would host our solar system billions of years later. Telescopes like the James Webb Space Telescope are now peering back into this formative era. Already they've spotted galaxies shining much earlier and brighter than theories once allowed, hinting that the first structures formed more rapidly than expected. These discoveries challenge our models and remind us that the early universe still holds surprises. The delicate balance of those early conditions is striking. Had density fluctuations been slightly smaller, matter would never have clumped into galaxies. If they had been larger, the cosmos might have collapsed into black holes before stable structures could form. The difference between emptiness and structure, between lifeless gas and a universe full of stars, was written into those faint ripples of the microwave background. What began as a hot, opaque plasma cooled, clarified, and gradually assembled itself into the luminous structures we recognize today. This was the foundation, the making of matter, the release of light, the dawn of stars. Every galaxy, every planet, every living being traces its origin to these earliest chapters, and yet this visible transformation is only half the story. Beneath the galaxies lies a deeper mystery, one that outweighs all the stars combined yet remains unseen. To truly understand how structure emerged, we must look to the invisible framework holding it all together. Stars and galaxies dazzle the eye, but they're only a fraction of the story. Astronomers now know that the visible cosmos, planets, gas, and shining suns, amounts to less than 1 part in 20 of what actually exists. The rest is dominated by something we cannot see, an unseen mass that outweighs normal atoms by more than 5 to 1. This hidden component, called dark matter, has quietly shaped the universe from its earliest moments. The first hints came in the 1930s, when Fritz Zwicky studied galaxies orbiting inside the Coma cluster. By Newton's laws, they were moving too fast to be held by the visible stars alone. Something massive and invisible had to be anchoring the cluster. At the time, his claim of missing mass was radical, but later work confirmed it. Decades after Zwicky, Vera Rubin and Kent Ford turned their attention to individual galaxies. They mapped the speeds of stars at different distances from galactic centers, expecting to find a sharp drop in velocity at the outskirts. Instead, the rotation curves were flat. Stars far from the core raced around just as quickly as those near the middle. The luminous disks weren't nearly heavy enough to explain this. Each galaxy had to be surrounded by a vast, unseen halo of matter. Imagine a swarm of fireflies glowing inside a transparent glass dome. To an outside observer, only the flickering lights are visible, but the dome itself holds the swarm together. In the same way, galaxies are fireflies bound inside an invisible enclosure of mass. This hidden substance does not shine, absorb, or reflect. Its only obvious signature is gravity, and yet that pull has determined the grand architecture of the cosmos. In the early universe, before atoms even formed, the invisible mass was already collapsing into clumps. Ordinary gas, still tied to radiation, couldn't gather on its own, but it fell into these gravitational wells once free to do so. Those wells became the seeds of galaxies. Without them, stars would never have assembled. The comparison to scaffolding is apt. A building rises around beams and supports that will later be hidden from view, yet without them the walls would crumble. Likewise, halos of unseen mass provided the skeleton around which luminous galaxies grew. Evidence for this framework doesn't end with galaxy rotation. Colliding clusters reveal the same story on much larger scales. When two clusters crash, their hot gas clouds slam into each other, slowing down and heating up, glowing brightly in X-rays. Galaxies themselves slip past with a little resistance, but gravitational lensing, the bending of background light by mass, shows that most of the matter sails straight through, accompanying the galaxies rather than the gas. The bullet cluster is the textbook case, the visible and invisible components clearly separated, revealing that the bulk of the mass interacts little beyond gravity. Gravitational lensing more generally has become a powerful cosmic detective. Light travelling from distant galaxies is subtly stretched and distorted by massive structures along the way. By analysing those distortions, astronomers can map the mass distribution of the universe. Time and again, the maps show that most of the matter lies in vast, invisible envelopes surrounding galaxies and threading between clusters. Even the oldest light confirms this picture. The cosmic microwave background, relic radiation from just 380,000 years after the beginning, carries a fingerprint of the universe's ingredients. Satellites like Planck and WMAP have measured these ripples in extraordinary detail. The patterns only make sense if nearly 27% of the cosmos is this hidden mass, while ordinary matter contributes just 5%. Remove the invisible component and the predictions collapse. Closer to home, our own Milky Way provides a vivid example. The stars and gas that form its glowing spiral disk account for only a small fraction of the total. Enveloping it is a massive halo of unseen material, extending hundreds of thousands of light years. This halo not only keeps the galaxy stable, but also shapes its future, guiding the eventual merger with Andromeda billions of years from now. Computer simulations bring the role of this substance into sharp relief. Models run with only ordinary matter yield a universe of diffuse gas, without filaments or galaxies. Add the invisible majority, and the cosmic web appears. Dense nodes, sprawling filaments, and vast voids, all in remarkable agreement with what telescopes actually observe. What exactly makes up this ghostly mass remains one of science's great unknowns. Some theories point to exotic particles like WIMPs, which would interact only weakly with normal atoms. Huge underground detectors shielded from cosmic rays have searched for the tiniest flashes of light from rare collisions, but results remain elusive. Others propose axions, ultra-light particles that might pervade space like a field. Even more radical ideas suggest that gravity itself may need revision. None of these possibilities has yet provided a definitive answer. Despite our ignorance of its true identity, the influence of this hidden majority is beyond doubt. It is the silent framework of the cosmos, the invisible stage on which every galaxy performs. Without it, the night sky would be empty, a universe of hydrogen and helium drifting aimlessly. In truth, the phrase dark matter is almost misleading. The important point is not that it is dark, but that it is dominant. Everything luminous is secondary, arranged and guided by a force we cannot see. This realization reframes our perspective. The universe is not made primarily of the stuff we know, but of something else entirely, something that refuses to reveal itself directly. And yet, we can trace its handiwork. We see it in the speed of stars, in the separation of colliding clusters, in the delicate ripples of ancient light, and in the vast filaments that thread galaxies together. To understand those filaments, the great network connecting everything, we must now step back and view the universe on its largest scales. That vast structure, known as the cosmic web, is our next destination. On the largest scales, the cosmos looks nothing like the scattered stars we see in the night sky. Instead of being evenly spread, matter arranges itself into a vast network, a structure stretching across billions of light years. Galaxies, groups and clusters collect along immense strands, while enormous voids open up between them. Seen from afar, it resembles a three-dimensional spiderweb, with glowing knots connected by delicate filaments of gas and unseen mass. This interconnected framework is what astronomers call the cosmic web. The story of how such a pattern emerged begins with the faint ripples imprinted on the cosmic microwave background. Those small variations in density, just 1 part in 100,000, acted as the seeds of everything to come. Gravity pulled matter toward the slightly denser regions, amplifying the differences over time. Like rain flowing downhill, gas and galaxies drifted toward the deepest valleys of the gravitational landscape. Over billions of years, this process produced the intricate arrangement we observe today. Computer simulations have been crucial in revealing how the web develops. Run a model with just the laws of physics and the initial density variations measured by Planck, and the result is striking. Filaments appear naturally, weaving into knots where clusters form, leaving vast voids in between. The simulated universe looks almost identical to what telescopes see when they map galaxies across billions of light years. The match between theory and observation is one of the great triumphs of modern cosmology. These strands are not empty highways. They're filled with tenuous gas, heated to hundreds of thousands or even millions of degrees. Known as the warm-hot intergalactic medium, this material is too diffuse to shine brightly, but it contains a significant fraction of all ordinary matter. In fact, much of the missing baryon problem, the long-standing question of where half the universe's normal matter was hiding, has been solved by tracing this hot gas within filaments. Though nearly invisible, it outweighs the stars in all galaxies combined. Detecting such faint material requires ingenuity. One approach uses gravitational lensing, the bending of background light by mass. When entire filaments sit between us and distant galaxies, their combined pull subtly distorts the shapes of those background sources. By stacking and analysing thousands of such distortions, astronomers can build maps of the otherwise invisible strands. Another technique relies on fast radio bursts, brief millisecond flashes from distant galaxies. As these signals pass through the intergalactic medium, they are delayed by the electrons they encounter. Measuring the delay provides a census of the hidden gas along the line of sight, confirming that the filaments contain the missing matter. These structures also act as the highways of galaxy growth. Gas flows along the strands, feeding galaxies with fresh material for star formation. Galaxies located within filaments tend to remain active longer, sustained by a steady supply of fuel. In contrast, those marooned in cosmic voids gradually starve, their gas exhausted, leaving behind old red stars. In this way, the large-scale architecture determines which galaxies thrive and which fade. Even our own Milky Way is part of this network. Our galaxy resides on the outskirts of a filament leading toward the Virgo cluster, part of a larger arrangement called the Laniakea supercluster. Within this region, tens of thousands of galaxies are streaming along the strands, drawn by the combined gravity of massive nodes. From our position, we cannot see the whole picture directly, but by measuring the motions of galaxies, astronomers can trace the flow and reconstruct the underlying web. The scale of these features defies easy comprehension. Typical filaments stretch for hundreds of millions of light years, containing thousands of galaxies. The largest known structures, such as the Sloan Great Wall or the Hercules Corona Borealis Great Wall, extend for billions of light years. To put that in perspective, light travelling at 300,000 kilometers per second takes 10 billion years to cross the Hercules corona borealis structure, nearly 3/4 of the age of the universe itself. Such immense walls of galaxies push against the limits of our theories. According to the cosmological principle, matter should be roughly uniform when averaged over very large scales. Yet these gigantic features seem to challenge that assumption. How could gravity, limited by the speed of light in just 13.8 billion years of time, build structures so vast? The existence of the largest walls may require refinements to our models of cosmic inflation or even new physics. Despite their immensity, the strands are not static. Simulations show that matter continues to flow along them, feeding clusters and draining voids. Over trillions of years, as dark energy accelerates cosmic expansion, the filaments will stretch and eventually snap, isolating clusters into island universes. For now, however, the network remains connected, channeling matter like a vast circulatory system. The similarity between this cosmic structure and biological networks is striking. Microscopic images of neural tissue, with nodes of neurons linked by axons, look uncannily like maps of galaxies connected by filaments. Even the distribution of dark energy in galaxies bears resemblance to the internal structure of living cells. While the processes are entirely different, the repeated patterns hint at deeper mathematical principles governing the growth of networks across scales. Observations of galaxy properties within these environments confirm that the large-scale context matters. Galaxies embedded in dense knots often undergo violent mergers, leading to bursts of star formation or the growth of massive black holes. Along the quieter filaments, steady streams of gas nurture more gradual development. In the lonely voids, isolated galaxies evolve in near solitude, telling different evolutionary stories. The web not only organizes matter, but also dictates the histories of the systems within it. The discovery and mapping of this grand architecture has fundamentally changed our view of the cosmos. Rather than imagining space as a random scattering of galaxies, we now understand it as a connected whole, where every luminous island is part of a larger design. Our position within it, in a modest spiral galaxy on the edge of a filament, provides perspective on just how vast and structured the universe truly is. Ultimately, the cosmic web is both a scientific and philosophical revelation. Scientifically, it explains how tiny quantum ripples grew into the largest structures ever seen. Philosophically, it shows that even the emptiness of space is patterned, woven into threads that bind the universe together. Among the largest gatherings in the universe are titanic associations, where hundreds or even thousands of galaxies are bound together by gravity. These are not loose groups like the local group, where the Milky Way and Andromeda share a quiet suburb of the cosmos. Instead, they are bustling, high-density regions, more like cosmic downtowns filled with interactions, mergers, and colossal amounts of hot gas. Astronomers call them galaxy clusters, and they represent the universe's most massive gravitationally bound objects. The scale of these environments is staggering. A single one can span 10 million light-years across and contain material equivalent to a quadrillion suns. The galaxies we see, spirals, ellipticals, and dwarfs, are only a fraction of the story. Far more mass is tied up in the invisible halos that surround them, as well as in the vast reservoirs of superheated plasma that glow brightly in X-ray wavelengths. What holds it all together is gravity, pulling not just on stars and gas, but on the unseen framework that makes up the majority of the mass. The Virgo collection, located just 54 million light-years away, provides a nearby example. At its heart lie enormous elliptical galaxies, each hundreds of thousands of light-years in diameter, surrounded by thousands of smaller companions. The region acts as the central hub of our own larger neighbourhood, the Laniakea supercluster. Even though our local group sits on the outskirts, the pull of this massive congregation influences the motion of the Milky Way itself, drawing us toward Virgo at hundreds of kilometers per second. One of the defining features of these cosmic metropolises is their hot atmosphere. Unlike the relatively cool gas inside galaxies, the medium between galaxies in such environments is heated to over 100 million degrees Fahrenheit. At these temperatures, atoms are stripped of their electrons, forming plasma. Though this material is invisible to ordinary telescopes, space-based X-ray observatories reveal it as enormous glowing halos that stretch across millions of light years. This hot medium contains more mass than all the galaxies combined and plays a decisive role in shaping their fates. The physics of these environments is extreme. When a smaller system falls into a larger one, its gas is compressed and stripped away by the high-pressure plasma, a process called ram pressure stripping. This often halts star formation, leaving behind quenched galaxies dominated by old stars. The effect explains why many galaxies in dense regions are ellipticals with little gas, while spirals, rich in gas and star formation, are more common in quieter neighbourhoods. In this way, environment dictates destiny. Collisions between these colossal gatherings are among the most violent events since the early universe. When two giants merge, the galaxies themselves usually pass through one another with minimal direct collisions, since stars are relatively far apart. But their hot gas clouds slam together at thousands of kilometers per second, creating shock waves that ripple through space for millions of light years. The resulting turbulence can heat plasma further, trigger bursts of star formation, and even reshape the distribution of the unseen mass. The famous bullet system is a striking example. In this case, two massive gatherings collided head-on. The galaxies, being compact, continued along their paths with little effect. The hot gas, however, lagged behind due to friction, while gravitational lensing maps showed that most of the mass followed the galaxies rather than the gas. This separation provided one of the clearest demonstrations that invisible matter dominates these systems. Without it, the observed motions would be impossible to explain. Such collisions release staggering amounts of energy. In the system known as MAX-J 0717, four massive gatherings are colliding simultaneously, creating a maelstrom of turbulence and heating. The energy released in these events can exceed that of billions of supernovae. On scales of hundreds of millions of light years, the temperature of the intergalactic medium rises, suppressing the ability of galaxies to form new stars. These violent interactions reshape entire cosmic neighbourhoods. Even in the absence of collisions, life inside one of these immense congregations is harsh. Galaxies are constantly interacting, tugging at each other gravitationally. Smaller systems are often cannibalized by larger ones, stripped of stars and gas until little remains. Some galaxies are stretched into long streams, their stars forming faint arcs that curve through space. These stellar remnants become part of the diffuse light that fills the central regions, a faint glow produced by stars no longer bound to any single galaxy. The brightest members of these assemblies are often giant elliptical galaxies that dominate their centres. Formed through repeated mergers, they can be 10 times larger than the Milky Way, with masses exceeding 1 trillion suns. Their central black holes are also outsized, sometimes reaching tens of billions of solar masses. These active nuclei can unleash powerful jets that extend for hundreds of thousands of light years, injecting energy into the surrounding plasma and preventing it from cooling. In this way, black holes act as thermostats, regulating the growth of galaxies in their vicinity. Observations across the electromagnetic spectrum have revealed new details about these cosmic cities. Radio telescopes detect relics of past collisions in the form of diffuse radio halos, caused by electrons spiraling through magnetic fields. gamma-ray observatories search for signatures of exotic particle interactions within the densest regions, and X-ray instruments map the temperature and density of the plasma, allowing astronomers to weigh these systems with remarkable precision. Measuring their mass is crucial because it connects directly to cosmology. The number of massive gatherings that exist and how they grow over time depends sensitively on the balance between matter and dark energy. By counting them across different epochs, astronomers can test models of cosmic evolution. Current surveys indicate that their growth has slowed in the past few billion years, consistent with the idea that dark energy is accelerating the expansion of the universe and pulling structures apart. Despite their harsh environments, some galaxies within these regions still manage to thrive. When a gas-rich spiral plunges into the dense core, it can experience a sudden burst of star formation triggered by tidal interactions. Though brief, these starbursts can produce thousands of new stars per year, transforming the galaxy before it is eventually stripped bare. Others, located in quieter outskirts, may continue forming stars at moderate rates for billions of years. This diversity highlights how location within these environments influences evolution. From a broader perspective, these titanic gatherings act as the anchors of the large-scale structure. They sit at the nodes of the cosmic network, connected by filaments of galaxies and gas. Matter flows along these strands, feeding the giants and deepening the voids between them. In this way, they are both products and drivers of the universe's architecture. Astronomers have even identified examples where the central regions host not just galaxies and plasma, but also enormous reservoirs of molecular gas. These rare cases show that under certain conditions, even the harshest environments can nurture new star formation. They remind us that the story of galaxy evolution is complex, shaped by both nurture and nature, by environment and internal dynamics. The study of these colossal communities has advanced dramatically with modern observatories, but many questions remain. How exactly does the balance between heating and cooling in the plasma regulate star formation? What role do magnetic fields play in shaping the diffuse radio structures? Could the densest regions provide indirect clues about the true nature of unseen matter? Each of these questions ties the local physics of galaxies to the broader puzzle of cosmology. In the end, these immense congregations are more than just gatherings of galaxies. They are laboratories where gravity, gas dynamics, black hole activity, and cosmic evolution all intersect. They embody the complexity of structure formation on the largest scales accessible to observation, and they remind us that our own galaxy, peaceful in its suburban filament, exists in sharp contrast to the crowded hubs where cosmic life is far more turbulent. As we zoom out from these colossal gatherings to consider the universe as a whole, a larger picture comes into focus. The knots of galaxies, the strands that connect them, and the vast voids in between all work together to form a coherent structure. To understand the meaning of this structure and what it reveals about the ultimate fate of the cosmos, we must now step back even further. The journey leads us from these immense congregations into the vast stage on which they reside, the universe in its entirety. When astronomers attempt to map the cosmos, they eventually encounter a fundamental boundary. No matter how powerful the telescope, no matter how clever the observing strategy, there is a wall we cannot see past. This is not because the universe ends there, but because light itself has limits. Beyond a certain distance, photons have not had enough time to reach us since the beginning of cosmic history. That distance defines the edge of the observable universe, a sphere centered on Earth with a radius of about 46.5 billion light-years. The finite speed of light turns the night sky into a time machine. Looking out is equivalent to looking back, because photons from faraway galaxies began their journey billions of years ago. The most distant systems observed today reveal the universe, when it was only a few 100 million years old. Push further, and instead of galaxies, we find a faint afterglow, the cosmic microwave background. This radiation, released 380,000 years after the beginning, marks the moment when free electrons combined with protons to form neutral hydrogen, allowing light to travel freely through space for the first time. Before this era of transparency, the cosmos was a glowing plasma in which photons scattered endlessly, unable to travel far. For that reason, the afterglow acts as a veil. We cannot directly see further back with light. Behind it lie the so-called Dark Ages, when matter existed but no starlight yet shone to pierce the fog. To study earlier times, astronomers turned to indirect methods, such as theoretical models of cosmic inflation or attempts to detect gravitational waves from the very first instance. The fact that there is a horizon has deep consequences. It means the map we build is necessarily incomplete, covering only the portion accessible to us. Beyond the horizon, space continues, but its contents are forever hidden. The observable universe is like standing in a valley shrouded by fog. We can describe the mountains we see, but we cannot know how far the range extends in every direction. Current measurements of geometry suggest the landscape is flat, which in cosmological terms points to an infinite extent. If that is true, our sphere of observation is only a minuscule fraction of an endless whole. Even within the visible portion, the numbers are overwhelming. Observations with Hubble and more recently the James Webb Space Telescope have revealed that galaxies fill every patch of sky, no matter how small. A region no bigger than a grain of sand held at arm's length contains thousands of galaxies when examined deeply enough. Extrapolating across the entire sky, the observable universe likely contains 2 trillion galaxies, each with hundreds of billions of stars. The diversity is immense: compact dwarfs, giant ellipticals, graceful spirals, irregular systems torn by mergers. Every one of them is a cosmic experiment, running its own version of stellar evolution. These galaxies are not sprinkled randomly, but arranged along the immense framework we explored earlier: filaments, walls, and voids forming a colossal web. Within this architecture, gravity sculpts matter into knots that glow as galaxy congregations, while vast voids expand into immense regions almost empty of stars. The pattern resembles biological systems, hinting at mathematical laws that produce similar structures across wildly different scales. By studying these arrangements, astronomers learn not only about the present universe, but also about its history, since the web grew gradually from the tiny density ripples visible in the microwave background. On even larger scales, the cosmic map reveals immense walls that stretch for billions of light years. The Hercules Corona Borealis Great Wall, the largest confirmed structure so far, spans 10 billion light years, nearly a tenth of the observable universe. Its sheer size challenges existing theories, because gravity should not have had enough time to coordinate matter on such scales. Features like this push cosmologists to refine their models, consider alternatives in the physics of inflation, or explore the possibility of statistical flukes in our particular observable patch. Whatever the explanation, the fact remains: the cosmos is organized into structures that test the limits of human comprehension. And yet, the map also includes emptiness. Vast voids stretch for hundreds of millions of light years, with only a handful of faint galaxies scattered within them. The Bootes Void, sometimes called the Great Nothing, exemplifies these cosmic deserts. Living inside such a region would produce a profoundly different night sky. Instead of thousands of galaxies, only a few faint smudges would be visible, leaving the impression of an isolated universe. The contrast between crowded hubs and these immense empty expanses underscores how unevenly matter is distributed. The environment within each type of region dictates how galaxies evolve. Those embedded in dense knots undergo frequent mergers and are often stripped of their gas, leading to old red populations. Those along filaments continue forming stars, nourished by streams of infalling material. Those in voids evolve slowly and in solitude, retaining gas reserves far longer. This diversity illustrates how cosmic geography acts as destiny, shaping the evolutionary paths of galaxies just as climate and landscape shape ecosystems on Earth. Even the so-called ordinary matter is not evenly visible. For decades, astronomers could account for only half of the expected protons and neutrons predicted by models. The solution came from studying the tenuous gas in filaments, detectable through subtle distortions in cosmic background light and the dispersion of fast radio bursts. This hot intergalactic medium contains more mass than all stars combined. Far from being empty, intergalactic space is filled with reservoirs of matter that continue to fuel galaxies, regulate star formation, and influence the future of structure growth. The broader cosmic census shows that ordinary matter is just a small slice of reality. About 27% of the universe's energy budget lies in unseen mass, and nearly 70% in dark energy, the mysterious agent driving cosmic acceleration. Together, these components shape the ultimate fate of the cosmos. Without dark matter, galaxies would never have formed. Without dark energy, large-scale structures might have continued growing indefinitely. The balance between the two governs whether the universe will expand forever, slow and recollapse, or approach a cold, isolated state. At present, evidence points to an accelerating expansion. If this continues, the long-term forecast is bleak for large-scale connections. Over trillions of years, distant galaxies will slip beyond our horizon, leaving each surviving galaxy group alone in the dark. Filaments will stretch, knots will separate, and the grand web will unravel. The observable universe of the far future will shrink, not because space contracts, but because expansion pushes everything beyond reach. This projection raises profound questions. If the visible cosmos is just a small part of an infinite whole, then beyond our horizon there must exist regions fundamentally similar to ours, with galaxies, stars, and perhaps life. In fact, in an infinite space, every possible arrangement of atoms must occur somewhere. That implies the existence of exact duplicates of Earth, of our Milky Way, of ourselves, as well as versions where histories unfolded differently. In some faraway domain, dinosaurs might never have gone extinct, or civilizations may have risen millions of years before us. The concept stretches further in inflationary cosmology, where the rapid expansion in the early universe may have produced not just one infinite space, but many, a multiverse. Each region could have different physical constants, different numbers of dimensions, or entirely different laws of physics. Most would be sterile, but some might allow complexity to arise. In this view, our observable universe is just one bubble in a frothing sea of possibilities. While speculative, the idea underscores how much remains beyond reach. If you liked the video, don't forget to leave a like. It makes a huge difference and helps the channel grow.